James has been most renowned for his basically work on stationary the power of solid today, namely with the spaceship gasoline, making with basically Galaxies.
So thanks for inviting me. So gasoline is named the code. I cannot explain it as an acronym, but to do it so cool. And there's a cast of not quite thousands, but there's quite a lot of people involved here, and it's sort of accumulated to try to go students. So this code has been around in use since the mid-90s when it was an in-body code, and since about 99 it became a hybrid code. And at that time, the primary focus was actually Cosmology, Galaxy, which is back in the code. It has been used in star formation and protoplanetary disks and things like that, but I'm not going to talk about any of that today. So what I'm going to focus on is the way Baryons change the cosmological picture. So if you look at the large scales, then there's a depressingly good agreement with everything pretty much. And so when I was a grad student working with the illustrious Big Bond, back in the day when it turned off later in the day, there was this hope that you could do simulations and actually work out what the cosmology was by regular simulations agreeing with reality. But then WMAP came and did such a better job of measuring all the parameters than we could ever do with simulations that whole industry collapsed. And now everything just looks so good on large scales for LMC and cosmology. But when you go to small scales, you have to start dealing with messy baryon physics, right? And as you can see, we do a miserable job here. So here's one of our galaxies, Galaxy actually. And you're supposed to be able to tell which one's the simulated galaxy, which one's the real galaxy. Anyone want to have it there? Isn't it Baryons? Yeah, the one on the left. So what this illustrates is that I think that the field is maturing a little bit. It's no longer sufficient to just make a galaxy and make a good-looking movie and then say, well, they can't look like galaxies, we can stop. You actually, there's now an onus on you to be able to create things that can be compared directly with observations. And a real step forward in this has been the development of the sunrise code by Patrick Johnson. This is how this image was created. It can create images of galaxies or anything simulating in different bands, any band you like. You can even put in dust. You can see that there's a little bit of dust in here. And it does multicolorated transfer and makes really gorgeous images. It used to be very slow, like it would take a day to make an image with a high degree of fidelity. But he worked on it now in about 10 minutes. So it's really great. And I'm actually going to teach a course on this, on galaxy formation, or that have the students do, since some of them are observers, is actually play with taking simulations and making them look like observations and then maybe reducing them a bit. So I think it's kind of
Do you do post-processing clumping or other stuff, for example, if you really want to become sophisticated?
No, you could play with the sort of optical depth you assign to region. The way Sunrise works, it grids the data up, and so you have a lot of control over how that works. The dust lanes, for example, are just assuming it's dust fraction of the gas. So I just wanted to highlight that they seem identical to images of real galaxies, and this is continuing in the grand tradition of scanning everybody by showing things that look pretty, and then glossing over all the issues with whether they actually match real galaxies. So what I want to talk about is how these things don't actually match real galaxies, and progress that's been made in the last 10 years or so in kind of resolving these issues. And so one of the big issues which has been resolved, I think, for a while now, but it was one of the outstanding ones, was the idea of missing satellites. There was this argument that dark matter predicts many satellites, and we don't see them around observed galaxies. There's the angular momentum catastrophe, which has had different names depending on who's presenting it, and that's been around for quite a while, and I think it's fair to say that that's well resolved now. There's dark matter profiles, observed dwarf galaxies versus the cusps that dark matter would predict. And too many baryons, but also too many baryons. simulated galaxies, they keep gas and they keep making stars. So that we have this issue with how do you get the star formation to stop? You can make it start just fine. How do you make it stop? So the missing galactic satellites issue comes from people like Ben Moore, who were doing huge simulations actually with the open star line PK2, which is the pictures of gasoline. And they found that when you do things, this is a local group simulation, you actually get enormous numbers of satellites in the dark halos. And so they looked at that, and they plotted up, and they said, look at all these satellites, why don't we see those around the Milky Way? What's going on? Because when you plot the Milky Way satellites on the same graph, you see the cumulative numbers down by factors of 100 or so. And so, where are these objects? So that's a potential issue. So a lot of the goal is to try and kill ACDM in some way. So Ben Moore has been a big fan of trying to do this for quite a while. And so this was one of the things that he would hold up as a serious issue. Another one is the angular momentum crisis, also called the overcooling problem. We could call it the galaxy size problem. And this is simply that simulated galaxies tend to be too compact. When you simulate a galaxy, when this was first being done in the 90s, people found that they were systematically too small by about a factor of 10. You've got these compact nuggets that rotated typically too fast, and for a given luminosity, they were incredibly small. And so they didn't fit nicely on things like the Tully-Fisher Relation. And so you can describe this depending on what you want to attribute it to, a lack of angular momentum, or too much material becoming too centrally concentrated. It depends how you want to look at it. It's kind of a symptom of one problem, which is that the galaxies are just too compact. Another one is the structure of dwarf galaxies. So if you get halos, just dark matter halos on small scales, and you ask what their rotation curve should be, if you have an NFW, which is this curve here, the dotted dashed line, then you expect a rotation curve which isn't all that different to one for a large galaxy that flattens out and drops sharply in the middle. Whereas if you observe real dwarfs, such as DG1 Rotation Curve, you find that they have these very slowly rising rotation curves. And this has been interpreted as evidence that dark matter might not be cold, there may be some extra physics going on, which leads to kind of a scale being imposed in the middle of these galaxies. And another one is the star formation history. So this is one of our favourite swindles in galaxy formation. They're typically very expensive to do. So it's not uncommon for people to run for 6 months, for example, to do a simulation, so you often just have one. So you don't actually have any population statistics, and so you never have to answer difficult questions about what the global star formation history looks like. Because you just say, well, here's one object, and we never really know what the masses are, etc. So I can't put it on a luminosity function for you and work out what the total aggregate star formation is. However, if you do volumes such as I did with my student Xing Shen, then you find that systematically you can calibrate things so that things look quite well, quite good in terms of the star formation history down to low redshifts. And if you plot with the appropriate axes, then you can kind of hide the fact that you have a quite large discrepancy by a factor of 3 by the end. So that basically star formation is cruising along very, very well here, and then it just keeps on going, whereas in the real universe, the star formation rate really dives below around about a redshift of 0.5. So this is another problem that we seem to run into when we try and get the baryon physics in. So when we do galaxy formation with gasoline, we're working in kind of standard line-seeing cosmology, and the code is gasoline. First written by me, with Wadsley and Tom Quinn, and it's been extended recently to include more physics, such as metal cooling, which is what Xing did as part of the thesis. And also the star formation model has been refined somewhat by the work of people like Greg Stinson. And the key thing is to recognize that you cannot resolve the small-scale structure. So when you inject the energy associated with stellar feedback, if you just naively put it in, then the average density in the typical volumes you can resolve will be relatively high compared to the H2 region that the supernova and so on would go off in. So that in your code, that energy will be cooled away very quickly. So you have two choices. You can either just wait for the computers to get fast enough and resolve the H2 regions and do the supernova within them properly, etc., etc. or you can do a subgrid treatment to reduce the cooling locally when you know that there's actually a range of densities within the volume that you're treating. So that's what we do. We assume that, and the way that effectively plays out is that in the first 10 million years or so, the cooling is heavily suppressed, so you can retain the energy until it evolves to the dissolved scale. And there are a few parameters associated with that. A key one is the density threshold here. So initially, just resolution effectively limited us to a threshold of around 0.1 hydrogen atoms per cc. This is not voluntary by any means. This is simply, that's the densities we can dissolve. Now, of course, this is not completely crazy. It means that you only form stars in galactic disks, but you don't form them in any particular part of those disks. It means the entire fairly thick gas disk is eligible for star formation. So that means you form them in the right place as long as you're willing to close your eyes and say the right place plus or minus a few parsec. But as resolutions improve, we've now moved to a regime where we can form them above, say, 100 H atoms per cubic centimetre. So we're actually now putting a threshold at the transition between the cold neutral medium and the molecular gas. So that means that we have at least the prospect of clumping the star formation within some regions of those simulated galaxies that are realistic. Now, in the interest of full disclosure, we can't set the threshold much higher than that because of resolution constraints, but at least it's now in a more physical ballpark. We have an efficiency, which is an efficiency per freefall time. That I think is kind of non-controversial. Parameter, we also have stellar feedback. So stellar feedback is, it used to often be called supernova feedback, but through the work of people like Monty and so on, we now know that there are lots of other very important sources of stellar feedback. So rather than pretend that we're doing something very specific, we should admit that we're just injecting energy that supports the turbulence and temperature of the gas. And beyond that, it's unrealistic to suggest that we are precisely controlling the nature of that feedback. So we just tend to lump it under stellar feedback. And the numbers that we use have tended to increase over time. So 5 by 10 to the 50 Earths per solar mass of stars actually corresponds to about 100% efficiency if the initial ejection is solar supernova. Right? But when you include the role of UV and radiation pressure and rings and so on, then it's a fraction of the total energy available.
So this is the entire recipe. You don't try and carry, there is this amount of cold gas.
No. Yes. Yeah. This is the full extent of our multi-phase treatment, right? We say we have an unresolved low density phase, and that legitimizes a reduction of the cooling rate. We don't otherwise treat.
And what kind of resolution studies have you done? Was this stabilized? Or
so Stinson et al. Is a resolution study paper. It does stabilize quite well, but the rates do change slightly as you change these parameters. For example, the efficiency, we used to favor smaller numbers, but as you increase the threshold, then a smaller fraction of the disk star forms and you change. So these numbers are always in a bit of state of flux, and it's always calibrated by trying to get a Milky Way right.
And the feedback,
so they are sensitive to resolution. Feedback doesn't have any parameters in it aside from the energy.
well, I don't know if that's a big parameter, because that's the an efficiency issue without doing.
Yeah, so the feedback has been calibrated on getting reasonable dwarf galaxies mostly. It seems to be
by observations.
well, you simulate a dwarf galaxy compared to, because things like the Milky Way, you can't blow anything out of them with stellar feedback. Well, we don't think you can. So if you really wanted to change the star formation, it's hard in the Milky Way, so we tend to do that via an efficiency, where in a dwarf, we can really get stuff out. So in terms of getting a bursty star formation history, and in the right stellar content, dwarfs are able to calibrate that parameter fairly well.
And you don't, I mean, you may not know, but we've also been invoking the great Murray in terms of a prescription for enhanced feedbacks.
Right.
Muttering the words AGN, but it's actually still tied to the stellar feedback.
So, yeah, so all these feedbacks are correlated spatially with where the stars are, okay? So it's a generalized stellar feedback. So AGN is obviously locally, centrally concentrated. And we had a treatment for that we've had in for a couple of years. It's a grad student, former grad student from Seattle, Jill Delaware, who's been working on that. But we haven't really put that into our big galaxy model. She's been mostly looking at M sigma and kind of limited, rather than having to kind of clone a lot of CP with that, see what it does with that. We have some results that kind of is coming in. So in terms of resolving these issues, the missing galactic satellites, I don't think anyone was surprised really by the idea that when you have baryons and you want to talk about visible satellites versus the dark ones, the baryon physics changes the picture a lot, and you only form stars in the larger satellites, and it's very easy to damage the satellites in terms of limiting their ability to form stars or removing the gas. And so that you start with satellites up here. This is satellites detected through their star content, so the simulated satellites. When you have no UV and no feedback, you get a relatively large number of them. But with once you turn on UV, you can get rid of most of the smaller ones without difficulty. And when you have feedback, you can get rid of some of the intermediate sized satellites as well. So in that sense, I don't think anyone was particularly surprised that you expect a lot fewer bright satellites than dark ones. And there's a role being played by cosmic UV cell feedback, but also ram pressure and tidal stripping. And the first two are kind of obvious because they're relatively easy to model, at least at a crude level within a simulation. Things like ram pressure and tidal stripping are very sensitive to resolution. You actually have to get the hydrodynamics of the satellite falling through the galaxy. So normally we have sufficient resolution to do the whole galaxy or galactic disk reasonably well. With small satellites, that's challenging. So I think this area is still going to be a subject of ongoing research for a while. So really pin down how that works. And this is some results from Sarah Nickerson, who's now in Zurich and is a grad student with DG1 as well. And she was looking at
why is it turning over even with no UV, no feedback?
So this is
is that resolution?
Yes, yeah, probably resolution. Yeah. It's like a little dark color. Yeah, she had a cutoff of a certain minimum number of particles. So here's an example from some of her work, which is just coming out now. And so here's the surviving satellite. The black line is the orbit. So on the right-hand side, you have the radius, and it's doing this orbit. And the closer it gets to the center of the galaxy, the more it's disrupted and the material is removed. But this one stays fairly far out, so it's actually been survived for quite some time. And the green line is the population of stars that it manages to form. And so this one would be a surviving, fairly obvious satellite.
What's the dominant mechanism of removing gas?
Ram pressure, so we can combine tidal ram pressure.
So that seems some distribution of hot gas in the middle.
Right, so these are cosmological simulations, so we don't make any explicit assumptions in that sense, but it is sensitive to physics.
So that hot gas density is consistent with gravitational constraints?
Typically, well, I don't have any sense of this particular object, how well it is, how well it does.
But generically, you're sort of Milky Way size halos, which is like that.
Yeah, I think generally there's too much.
Yeah,
There's generally too much, so that the stripping would be higher. And yeah, we think, well, that's one of the things we lump under AGN Feedback. Want some way of giving it more entropy so that the halo is even more fused.
Sure.
And then
Well, one could believe that there is an additional entropy swap that might remove most of the baryons, but then your, as far as the dwarf galaxy is concerned, your stripping channel over is maybe less effective.
yeah. No, if the overall pressure stays high, ram pressure should still be pretty effective.
Well, no, that's, the D is given by the loss of dispersion halo, right? So the rho v squared that the galaxy feels would be dependent on the gas, pancake gas density.
That's true. So this object here is an intermediate mass guy, but this one is as well, and it depends on history. This one was started out a little closer to the main halo, and didn't really manage to form many stars. has some gas, which is the red line, and as it approaches the main halo, that was all stripped. So this ended up with a relatively high final mass, but with no star formation. This one had a nice, had a longer time to create some stars before it lost its gas. And so even though it was a smaller object, it managed to be released. So this piece of paper that's about to come out from Sarah's work. So in terms of the angular momentum crisis, or or the cooling problems, etc., it's been shown that resolution is a critical component, and that's simply due to numerical loss of angular momentum. The resolution is poor. You tend to find it hard to. It's not a conservation issue; it's a transport issue. You tend to transport angular momentum. You dump it in the halo rather than in the gas in the disk. And so as your resolution improves, you can make a more extended disk without this strong central concentration of material. Another issue is feedback. If you don't have effective feedback, then you tend to have heavy disks that transport a lot of angular momentum and become very compact. Whereas if you do have effective feedback, then you can get much more extended disks, effectively the same galaxy with an effective feedback recipe, slightly higher resolution, and it makes a nice extended disk. And the feedback helps keep the disk diffuse, but it also preferentially tends to eject low angular momentum material, allowing you to make a larger disk. So resolving that issue, I think, is now kind of straightforward. So this is these are two simulations of the same galaxy. The one on the left has a less effective feedback, so that most of the material tends to come into the middle before it forms stars. And this is the gas here, and this is visually what it looks like. And so you build quite a large bulge. And in terms of the central rotation, is quite high. So this has got quite a large bulge, it's sparred. And you can see the rotation rate on this guy is actually higher than the one in this one, where it has much less of a bulge. The star formation is much more dispersed throughout the entire disk of the galaxy. And it's a much more realistic property.
Holes that are being blown is basically the feedback.
It is
like super bubbles.
Yeah, it's super bubbles.
You're doing this with energy, right?
Yeah, with energy. But the cooling is turned off so that the energy is translated very effectively into momentum in a relatively short time. Right? So from that perspective, in terms of resolution, there isn't a big difference between momentum feedback and energy feedback in terms of the way it affects the galaxy. The main difference I would argue is that the efficiency is a function of galactic environment. Because we have a fixed effectively efficiency, whereas momentum feedback, we can argue, depends on whether it's started. So in terms of the resolution we have, I think they're somewhat equivalent to how they function.
Is there any long-term, large-scale spiral structure, or is it just totally transient?
We find it's transient unless there's a strong perturbation.
These are just isolated galaxies.
These are isolated in this case.
And don't have any sub-halos either.
No.
Has anyone ever found compact spiral structure without putting in a companion?
Not long lived. It's always tends to be transient.
So what was the adjustment you did to your feedback?
That was the higher threshold, the main thing.
So you concentrated the star formation in smaller spots.
Yeah.
So can I go back to that question? Is that considered to be a big deficit in SIM?
We've reached
If you don't have longer spirals unless you
No.
isolate them?
I don't think so. Well, you always have spiral structure, but it's not a problem. I don't think it's into a whole
Well,
spatial
they are.
area.
So if you say, how long do people think the spiral structure in our galaxy is?
I don't know.
We can have big depends. It's not an issue.
So you mean it's all being driven by Thursday and Friday?
No.
It's transient.
Wouldn't be the maximum spot.
Well, but
Is that right?
Small.
They're pretty big.
So I would argue that qualitatively this looks pretty good, but the onus is on simulators to get a little more quantitative, right? And say, well, how does it look in detail? And I think one of the things that messes people up initially is measuring things in simulations the way simulators measure them, and they're measuring observations in different ways, and then it's very hard to compare and determine whether there's a real discrepancy. So in recent time, we've gone over to things like the first image I showed, the sunrise representation of the galaxy. You actually convert things to an observational reference frame, and then do your measurements using Galactic or something like that, so more observations can be made. And when you take that approach, we can actually get on Tully-Fisher pretty well. The only thing I would say in terms of criticism of this is that these halos have somewhat been selected, right? These are the sort of the ones we like to simulate in a sense because they give results that we like. It's not kind of a blind sample. So I think going forward, there is some necessity to do more of a blind sampling approach to forming objects and get something you can compare more directly to a complete observation sample for halos. So these are Milky Way analogs, and these are the dwarfs.
So why did you get such a good visualization? What's the information?
Sorry?
What is the information input that allows you to get the picture in the simulation? Is it star formation?
So we used to systematically be too compact, and so it's a symptom of the fact that the disks now have much more reasonable scale lengths and distributions of stuff.
That comes out mostly because of the feedback.
Yeah, most the improved resolution and feedback, they both kind of go hand in hand with the better result. And also rotation curves. So this is a more direct demonstration of the effects resolution. So this is a 20,000 particle disk, gives you this very strong peak rotation curve. Sorry, this is the disk with no feedback effectively, so it becomes incredibly centrally concentrated. UV doesn't touch that much. You turn on some feedback, even at low resolution, numerical and angular transport still brings a lot of stuff to the middle, too much of a bulge. You go up to 160,000, you get something still centrally peaked. You get up above about 1 million, and you get something that's reasonably flat. So this is where we get this idea that you should have about 1 million particles in your particle simulation to get anything reasonable in terms of rotation.
Well, have you overshot in terms of resolution, or have you just arrived at a happy point?
Well, this is slightly older work, and at that point, it wasn't as clear whether we converged or not, but in their more recent work, it seems that we have. So I'll show some more resolution curve. And another one is the Size-Luminosity Relation, and this is some recent work by Alton Brooks. And here, they were simulating observations in the V-band using sunrise, they were fit with Galactic. So this is what happens when you get something like the Dwarf Galaxy, and you image it with sunrise. This is what it looks like based on an image-on. And then we put it on these relations to compare it to data that actually seems to sit quite nicely in the middle of the distribution. So some of our recent focus has been on dwarf galaxies. Now, the sales pitches that they're challenging, therefore we should do them because they're hard. They have low stellar masses, which simulations seem to have trouble with. Almost no bulge. Bulge is symptoms of problems with simulations transporting too much material. And they're very blue, so they've got the fresh star formation at relatively small rotation. So these are disk-dominated bulgeless systems, and we want to be able to get systems like this. Of course, if you flip it around, there's always a second explanation for everything, and the other one at the other end is that large galaxies are really, really hard, so we just do what we can do. So, dwarf galaxy cause, this was one of the other potential issues. So, Sergei Dushenko and I, with Hugh Cashman, showed in a simulation going to Redshift 5 that a dwarf galaxy was simulating cosmological, so no kind of cheating in that sense, around 10 to 9 solar masses. I was able to take what was a cuspy profile in terms of density versus radius and convert it into a chord profile. Right, so this is kind of the proof of the concept that it works. And the way that this works is that we have the red profile here being stars, we have bigger star formation. The galaxy is actually centrally baryon dominated. Those baryons are moving around at a fair rate. That rate in a dwarf galaxy is comparable to the dark matter velocity dispersion, so they couple quite well. And you can pump energy into the dark matter and effectively eject the very cold, sort of low entropy dark matter right from the cusp and just redistribute it out here. And so that worked quite well, but one of the issues, the criticisms of this work was, well, that's just some funny object that we've never seen in reality living at redshift 5. What about a local dwarf that has gone evolved for the entirety of the universe and undergone some late movements or whatever? And that's the thing that people actually observe and measure these chord profiles in MEV-BAT. And so last year we did do this. We tried to do a dwarf galaxy that would show everything all in one go. So we wanted to take it to redshift 0. We wanted to give us the star formation that matches observable properties of dwarfs. We wanted to be bulgeless, and we wanted to get a chord mass profile. And so this is the dwarf galaxy DG1. This is the Nature paper from last year. So I have a movie of this as well. So this is the object forming. You can see very early on in its evolution, the feedback is very vigorous. And so star formation doesn't get going in some regular fashion. It's very bursty, and it's really throwing material around, and those events are sort of, they're on the characteristics of the scale of the galaxy. This kind of vigorous feedback occurs in all galaxies, but the important thing is they have to occur on a galactic scale, shift a lot of the baryonic mass back and forth in a certain fashion, and then you get very strong coupling with the dark matter halo. It's also that the dark matter halo in the Milky Way has much higher velocity squares, it doesn't really care what the gas does. So as time goes on, we're forming a disk. The angular momentum vector of the disk changes quite a lot as this object undergoes mergers. And an important part of doing this to redshift 0 rather than stopping at redshift 5 is showing that those mergers tend to increase the profile. So when you take two chord objects and you merge them, you get a new larger object with a slightly larger core. So you can bring up the size of the cores even slightly larger than the ones that are able to do the early simulations. And then this thing eventually settles down and forms a dwarf with a quite large amount of gas in it, very extended disk, but the optical supplement region is relatively compact, and yet it's not super centrally concentrated. It's not actually forming a bulge. And it continues to happily evolve away. And you can see there's no bar or any bulge in forming this object.
So this is sort of like an LMC sort of thing?
Yeah, a little small. Yeah, an LMC would be like this structure is replicated quite well.
Is the object actually growing or is the scale changing?
Sorry? The object is growing, the distance is becoming more extended. The scale is fixed and physical.
So this is with one unique energy feedback description.
Yeah.
And
we would argue that AGN don't play any role.
No, I'm not.
So we're happy.
But the universality from object to object is a function of mass. So the efficiency of the feedback is there. The assumption you could check it by how many stars it produces.
Right. So as I was suggesting earlier, these simulations don't allow us to say all that much about the kind of global properties stuff, which is stripped down plot kind of question. So
Can you believe the distribution of the simulated stuff?
I think it's pretty reasonable. I'll show some more curves.
What's the definition of reasonable?
Well, I'll show you the bottom and show you everything. So here's the way the thing looks. This is so the thing's about 10 to 9 solar mass halo with a velocity dispersion of around 50 kilometers per second. And here's what the simulated thing looks like. This is the H1 map. It was made by Chris Brook, who is a kind of local sunrise expert within the collaboration. And you can compare it to sort of like Formula 2. And sort of visually, it looks very good. The sizes of the holes, the degrees of concentration of the gas look very good.
You start the simulation with full primordial complement baryon.
Yeah. Yeah, this is a Cosmology for Wadsley. There's no kind of special choices made.
So are you still turning off cooling?
Yeah, we always do that. So it's a relatively short time period, maybe 10 minutes. So here's the star formation history. You can see that the burstiness, which is characteristic of medium size dwarfs that we get these strong bursts and these periods of developing activity as the gas reaccumulates. So that aspect of the dwarf seems to be reproduced quite well. We get H1 distribution, which looks quite similar. We haven't really worked out ways to characterize that in a quantitative way, but visually it looks quite similar. When you look at the H1 turbulence, the feedback is able to generate a dispersion in velocity of the H1 within the dwarf that is quite reasonable in the observed regime. And when you look at the rotation curve, you have this nice slowly rising rotation curve. It's always a tricky business in these dwarfs because observationally, the scale length of order 1 will pass it to type 1 effect. But it does look quite good. These observations usually run out before you actually get to this one part of the curve. And a relatively small fraction of the gas is being turned into stars. The vigorous feedback is able to keep most of the gas kind of suspended and not really available for star formation.
What did your last sentence on slide mean about 30%?
The baryon fraction of the halo is a third of what you expect.
Yeah, so if you take omega baryon over omega matter, we have a third of that in this object.
But the guys that size observationally is even smaller.
Right. So
Still
injected a lot of baryons that just have to come back. So yeah, the feedback doesn't always inject them totally, but a large number have to remove. So this is what the gas density looks like. This is virtue 1.5, virtue 0.5. It's a little large disk. And I-band surface is shown here. This is the sunrise. So we're ending up with about 2 to 5 micrometer solar masses in stars, and I-band luminosity minus 16.8. It's quite blue the way you would expect. The disk scale length is reasonable, and the rotation curve is good. And so it's nice to have a Tully-Fisher relation. This is one of the objects I showed on the relation earlier. It's one of the dwarf dots. And so we're pretty happy with this. We consider this a success, and just to kind of rub it in a little bit, it really is a bulgeless object. There's really no evidence of a bulge or boxiness or anything in the isotopes and the surface. It's fit beautifully by the pure exponential. And that's true in pretty much any way you want to try it. And so it is a more sort of detailed attempt to fit a rotation curve using tilted ring analysis, which is supposed to be a more sophisticated observational approach. And you can see that we actually get a profile that's very comparable to an optical probe. We should be comparable to the DG1 curve as we work out. So here's a kind of rotation curves revisited as a function of resolution. So here's our kind of low-res case, the tan line here. You can see that it's kind of chunky because it's become essentially concentrated. So this one here is even worse. This is the low threshold feedback. In this case, the feedback is kind of evenly distributed throughout the galaxy. It doesn't do a very good job of moving gas around. It doesn't eat out the cusp. It doesn't prevent central concentration. And so this thing has quite a large bulge, as shown in this case here. And then, so you put decent feedback in, moderate resolution doesn't do a good job. You increase the resolution, and medium resolution case, you get the red curve, which looks already quite good. When you go to the full resolution, which is the blue curve, you keep a very similar profile. So in that sense, we would claim that we've converged because, at least in the rotation curve, it didn't evolve very much as we increase the resolution.
But if you change your no cooling period,
the no cooling period is set by a blast wave, CDOT blast solution. You don't actually hit that. It's just set by the local gas density. So it's determined by how long it should take the explosion to reach maximum size and start going to the cooling phase.
What's the black curve?
The black curve is the other case. So there's actually 2 dwarf galaxies in range, DG1 and DG2. So DG2 is a slightly more extended dwarf similar mass. And you can put it on the baryonic Tully-Fisher relation, let's say some of the spikes. And so this is the H1 plus stars in the disk versus represents the rotation, and dwarf sits right here. You don't have error blast stroke, because this is just going to be right spot. And in terms of the dark matter core, you can measure the inner slope of the dark matter profile, so the NFW, and there are similar other sort of dark matter power law type custom fits. They tend to have alpha values that are closer to, say, -6 or so. And as the galaxy evolves over time, sorry, they have alpha values at -1.675 redshift. And as the galaxy evolves, it starts to accumulate baryons. The purple here is star formation rate. It undergoes these starbursts, and the starbursts are instrumental in helping change the internal slope. So there's kind of two processes that are very closely related. There's kind of impulsive star formation that blows a lot of the mass out. You can also grind down the cusp by just kind of swashing back and forth. It doesn't necessarily shut off the star formation. And in terms of the distribution of angular momentum in this object, here are some measurements done by Frank Vandenbosch of real objects. And so here, these curves along the top are what you would infer from the dark matter halos that these objects live in, or what he infers the properties that are, if you've got that material and just let it sit at the radius set by centrifugal balance, you would expect the curve like the top one here, and the shaded area is what the real baryons do, and you can see that you have a real deficit of these lowering momentum baryons, and you can see that for our simulation you have a relatively similar distribution, such as the first box here, where you've really managed to kick out all of these lowering momentum baryons, and the high momentum ones haven't quite got in. They're sort of sitting out in the halo.
Is that because you kick them up before they get into the center, or lose angular momentum, or?
So there's definitely, you mean that these ones that didn't get in?
No, the stars. I mean, the gas that.
He's taking lowering momentum stuff at low degree on it, throwing out.
So this was thrown out as gas.
Okay, so the gas gets in with the custom profile, but then most of these.
Yeah.
So it's not like it's picked up before it gets in.
No. Yeah, you need it to be kicked out, otherwise you won't destroy it.
But you've labeled that stars. So there's still a lot of gas because the star formation is inefficient. So what is the remaining gas look like compared to the stars?
I'm not sure, but this is stars too, so it's comparing that. You can see from the movie below, the gas is in this kind of parabolic state being thrown out. So, and one remaining issue, which is the full disclosure part, is the dwarf galaxies are looking really good, but you go to larger scales and things aren't quite as good. So this is from Sajin's thesis. And so for relatively small halos, 10 to 9 solar masses, then you don't get a lot of star formation. So the dashed curve here is the fraction of the baryons in stars. It's the universal fraction here. So for these little guys, you can get a lot of baryons, and as you would expect. And her thesis was focusing on making rings, so this is where all the rings are coming out from, sort of intermediate mass halos. But as you get to larger halos, you have a lot of trouble kicking the baryons out. You can keep them all, and pretty much the algorithms will just happily convert all those into stars. So at pi redshift 0.5 or so, it doesn't look too bad, but there's a huge amount of time between 0.5 and now, and they just keep on making stars out of this. So you get quite a lot of excess in terms of star formation. And so this is the hard problem that makes us avoid large galaxies, that also can be more expensive to simulate. And so we need something else. And so what's often invoked is AGN feedback. So AGN feedback can create high velocities and in principle unbind a lot of material even from large halos. And this has been played with by quite a few people now. Voluntary done some work on this, and working with us as well. Ziana Di Matteo, working with Wolf Sprigel and his group has done some work. and Craig Bruce working with Rick Shea, his group has done some work on simulations trying to put in the AGN feedback. And numerically, however, it's very challenging. So, and the constraints on how you do this are rather poor, particularly how you get the whole process going in terms of making seeds. And so it's quite challenging, and seriously, if you're having fun in any regime where you're not well constrained, it's always fun because people let you publish anything. So the way we've done this is following the suggestions of Voluntary et al. We're assuming that these black holes are forming due to rapid collapse of fundamental gas clouds. And so you're establishing the black holes with relatively large initial masses of 4 to 10 to the 4, 10 to the 6 solar masses from the get-go. 10 to the 6 is kind of on the high side, except that that's kind of where a resolution tends to force us to act. And so the way we've implemented this is that when we have effectively primordial material, we assume that star formation much of the time results in intermediate black holes rather than stars. So there's not much star formation going on at this period full stop. But what this does do is give you a large population of intermediate black holes to kind of seed the process, and some of those hopefully then become available to become the AGN Results of Galaxy. And so we're doing Monty style accretion following D. Matteo et al. And we're doing feedback as heat following D. Matteo et al. We have been experimenting with trying to limit cooling to try and make that feedback more effective, to approach the limit if we had very high resolution. Though it's challenging to try and apply the kind of tricks we've done for stellar feedback because it's not as localized in time. So a single burst of energy is a more continuous process, and so it's not so obvious how you avoid cooling. And what would be the physical system we're going to do that? So some of our early results, our black hole formation is very much peaked at early times, around redshift 10 or so, sort of just on the cusp of reionization. We get a very large population of wandering black holes, and these things are not particularly good detections observationally. It's kind of a missing population in some sense. However, people have argued that ultra-luminous X-ray sources seen wandering through near the centers of galactic halos could be intermediate black holes, and so we're happy to wave ahead and say we find that because that's has wandered around in a similar fashion. We are finding that the subgrid accretion is hard to resolve. Well, it's hard to resolve the subgrid, it's also hard to resolve the densities required to really make that go at a reasonable rate to get Eddington type accretion rates. And feedback is quite effective. So this is work by Jill Bellaberry, who's just started a postdoc in Michigan, and actually we're thinking of trying to get her to visit in the next few months. And so the early results show that they start with masses around 2 by 10 to the 5, and that's mostly resolution constraint. We're happy to invoke models to argue why that's reasonable mass, but it's also where we're sort of forced to act. And then they grow up to 10 to 7 in reasonable time. This object here is the central black hole of this galaxy simulation. And we actually also find that the feedback is quite effective at kicking baryons out. So here's the universal fraction normalized to 1 here, and as time goes on, we've actually managed to kick out quite a lot of baryons via the AGN feedback. There are issues though, and one of the big ones is that the mass of the black holes is comparable to the mass of the dark matter particles, and so dynamic accretion just sort of doesn't work, right? Because dynamic accretion only really works if you're in a sea of lighter objects, so that's a bit of an issue. You can also have two-body interactions that will give more random motion to your black holes than you really want. So that this has been a huge challenge for every group trying to do this. I know some groups have done things like periodically stop the simulation, locate the black hole, and put it back in the middle of the galaxy, but that's not very appealing. So we're kind of trying to work on more physical approaches to dealing with that issue. And the other one is how to get enough growth in 10 gigayears to go from a reasonable seed to the largest observed black holes in CITA relation today, because typically we can't really resolve those nuclear regions where the feeding is going on, and really, so a lot of groups have a fudge factor where they arbitrarily increase the accretion rate to get the growth rates up to a reasonable number.
Well, James, it raises sort of a general question. I mean, there are these fudge factors. Also, I mean, realistically, there's no way the AGN is going to heat enough of the ISM to blow it up. That's just not going to happen with Galaxies.
Is there what's the second?
there's not enough energy being deposited in the gas in the interstellar medium by an AGN to heat it enough to drive it out.
Well, the energy is very directed.
Yeah.
It's like it works.
And it doesn't work because the gas cools.
That's why you need
That's why it
gas
turns off.
flowing in.
That's why everybody turns off the cooling. Okay, that's the problem. So what you're doing is you're using the heat to dump momentum into the gas.
Right.
That's why you're getting it to work at all.
Right.
Okay. But the physics, so it's just disturbing that, you know, you're using the wrong physics and it's known to be wrong. Right. And you tune things to make them look like real galaxies.
Yeah, well, with this kind of approach, I'm definitely a believer in the idea that you parameterize what happens rather than claiming that you're doing things.
Exactly. So that's the question.
These are somewhat flow models.
Right. I think that's something that should be stressed because a lot of people see that, for example, thinks it's a real model.
Yeah.
And it's just not.
Yeah, it's a flow model.
Yeah. So if you take it in that spirit, and you know, the
Well,
question is,
it's a ballpark.
if you tune it to get some things right, you can try to say that you can maybe predict some other things.
It's challenging, but we obviously want to get, you know, things like the down pipeline and so on.
Right.
We want to tackle that. We also want to get clusters and groups right, and you really need something like this.
Well, there's no question on larger, bigger nipples at the AGN, because by that time you get rid of all the gas returning to the star for some fraction. And the rest of the stuff you can pick up because it's small enough density.
Well, we need to get those.
Exactly. Then the AGN feedback, energy feedback really does matter.
Right.
You're
Yeah,
not
because
gonna-
groups and clusters without AGN feedback are disaster.
Right, exactly.
And we have some early MC relation plots here, so these sort of lossless versions of the masses. And so it's kind of all over the bit, but we don't have a very big sample yet. This is just one case.
Can you just add more North American particles?
So that's actually one strategy we're trying, is to increase the number of dark matter particles to try and, but we can't really bring it up to we can. I believe that we can get it to the level that we can suppress two-body problems, but I don't think we can get it to the level where the dynamic compression.
So are these cosmological simulations?
Yes.
So can you try to take those initial conditions and resimulate on smaller scales? That seems like the other way to do it, right? And just really.
So what I've hired some students to just get a little highly resolved halo and just see what it takes to get the dynamic compression,
Exactly.
what it takes under control. No one's actually done that. I mean, it'd be good to know what the white numbers are.
Phil, of course, is starting to do this. That's how you take the progress, right? Takes some cosmological simulation, pulls out, and then resolve it. So I think that
Yeah, I think
is
people
a
have
neat
to
way of going at it.
Well, exactly. They're toy models, but if you can clean it up, then you can get more predictive power. I think that's one of the things that needs to be cleaned up. There's too many feature areas there.
But you have, the black holes are actually evolving according to gravitational potential.
Yeah.
So you could put in an influence rate.
Oh, absolutely. That's
Yeah,
what I want.
it's
That's what I want to have the
right.
student do. Absolutely. I want the right chapter to be
That's
trained
actually not something that would cause huge problems.
No, that should help clean it up a lot. I'm surprised on this.
I mean, it's probably a fairly simple application for your people to do.
Well, exactly. So it's hard to
It has the advantage of actually has reset.
Yeah, exactly. You want to eliminate that stuff where you change the scale of things. You got to rejoin.
The only trick about the dynamic perfection formula is in principle they're an envelope of space. So you have to work out to what extent you can fudge that. But probably,
But you have knowledge of the local gravitational potential.
yes, you can say, and
That's
probably should be able to use that to get a sense of how large the object really is and get that land factor, the log factor. So I'm pretty confident with this. So future work. So at McMaster, Greg Stinson gave a talk on this already. We have this mud sample, which is an unbiased sample of galaxies we're simulating. The idea is we want to try and see where you sit on things like the Tully-Fisher relation. If you don't pick the good objects that work out well, and because I think that there's kind of a calibration error potentially that we still have to be sorted out. We're doing H2 formation now as a precursor to star formation. Charlotte Christensen has been doing this in Seattle. We want to do some radiant transfer. These two things are coupled. H2 formation without radiation is kind of silly. So we want to do those two things together. We've already done some of this with protoplanetary disks. We might transfer it to cosmology along the lines of.
So what are you doing, like ray tracing, or are you doing
Flux and
distribution?
So we're thinking of operating it. So the way the cosmological stuff. And of course AGN feedback and galactic output. So we're quite confident actually that our approach to stellar feedback is good, and you don't need ad hoc galactic outflow model. You can get several hundred times per second outflow without any difficulty with the first principles. So we don't really think you want to add outflow models. We don't believe in that. And as you know, as the computers get faster and the codes start to do the scaling a little better, we like to do live objects like the large galaxies and cosmos. But at the moment, it's very small.
So you're getting a couple hundred kilometers a second in your dwarfs?
In the dwarfs, yeah, but in large galaxies, we have seen winds up to 1,000 in the large galaxies.
Probably from the supernova.
And the stellar feedback. Yeah, it's really hard to get. I think supernova are probably instrumentals that really fast moving. It's really hard to get them the other way. So I wanted to finish with a movie. This is just a Milky Way analog rather than the dwarf, but it's quite nice. And this is just to show that in our recent work we can get relatively relatively low bulge-to-disk ratios, even for large objects as well. And even things like mergers, if you have enough resolution, are not able to drive everything to the middle and force the formation of large bulges. And, so in this movie, the gas is shown as sort of greeny color, and the reddy blue here is stars, and they're colored by age, so the disks are preferentially redder, bluer, sorry, with the stuff next to it. You can see these tails of ejected stars in red. And so these two objects will undergo a merger. You can see this is orthogonal to this one more or less. And so they have a nice big merger here. So they throw a lot of stuff around, they create a nice big stellar halo, but then they happily form a disk without much of a bulge. It seems like with enough resolution, and that's really mostly what it is, you can get quite reasonable on galaxies. So we can't claim that that's terrible clever introduction to physics or anything. So I like to leave it.
We have time for a few questions.
So detailed stream work within, let's say, the Milky Way using simulations like this. I'm not sure if I want to come across the view that it's hopeless or that it's promising. What do you do there?
So what are you trying to get from the streams?
You're trying to get a dynamical interior snapshot of the galaxies that you're saying something about.
Reconstruct the merger.
I think that's very difficult. I mean, I've talked with a few people trying to do that. It seems really hard. You can't go back more than one orbit or so. I think.
Yeah, but the data is going to improve enormously. The question is, will the simulational part be able to handle it?
Yeah, I think it's an addition. I think they make perfect use of it.
Okay, on a related vein, I think what I'm taking from this is that any comments on galaxy formation using the very large box simulations that people are comparing with observation, you would say are all premature and that premature first.
I think they're a little premature, but the thing is that when you can constrain the galaxy in several different ways, I think it becomes more reasonable because we know that every object, we have things like the relationships between the rotation curve and stuff, which is really something. So if you can do multiple constraints, then small samples are still interesting. It's when people do, single galaxies and put them on one observation plot and then say, oh, it's great.
Oh, no, that's not what I meant. You see, you are doing constrained simulations here, which is where you can get the number of particles. So what I'm thinking of 400 megaparsec boxes or more, and you're still saying it's going to be able to say something about the galaxy?
I think it's really hard because then the resolution just dies and they become practical.
Okay.
So at some level though, we can tell which properties of the galaxies are more robust. So total star formation history seems to be somewhat robust. So it's not pretty, it doesn't look like a nice disk, but total number of stars.
Are you using the growth of metallicity as a constraint both within the galaxies and in the objective material?
Yeah, we have been trying to use that.
And what does that tell you?
So that was Sachin's thesis more or less. Those numbers seem pretty good in terms of we seem to saturate at the right melodies in most objects. Even margin we seem to do pretty well. It gets a bit more tricky when you try and look at these melodies of outflows and melodies of function of distance from the galaxy and things like that. Those observations are harder to interpret in a really quantitative way.
Well, what do you predict for the outflow levels?
Well, the usual number is around 10 to the minus 2 solar, which is what we get.
For the outflows from the dwarfs.
The dwarf.
Well, it's 10 to the minus 2 solar, you think. That's the outflow metallicity? Or what kind of galaxy? I guess you're only really getting outflows from dwarfs.
We get outflows up to around 10 to 11 solar mass.
And then for the halo mass.
Yeah.
You're not trying to, a lot of outflows you've seen in galaxies locally that have 10 or 12 solar masses. Those metallicies are solar or even super solar.
It's very challenging to get the high wind velocities, so it's hard to get the outflows from large galaxies because they have very high resolution. But then you're just talking about a single object in the zoom simulation. It's harder to relate that to high.
Right.
So that's one of the problems where the boxes have really full on. So it's hard to relate. So we were doing boxes, but we decided to focus on high resolution so that people can understand the outflows before we go back to the class.
Those compact, I don't know what color, the color of the gas,
3D so
compact blobs of gas, is there a core inside of those or is it just gas?
they're all dark matter halo.
And would they be candidates, if they're falling into the galaxy, candidates for high velocity clouds?
These ones are relatively large. I don't think that we can do this.
Because that's a redshift zero phenomenon that we observe. There's different about metallicity. Maybe not a lot about the mass, because you can only trace it in the neutral gas.
Right. Yeah, we haven't really had anyone look at that in detail. We probably should.
Are the high velocity clouds supposed to be part of the broken up stream? Or are they
So actually that raises the question I'm going to ask you. So, there's been a lot of data has been pushing this cold flow and so forth. Do you guys see this phenomenon?
Yeah, we agree pretty well. Kind of like it. My only concern is whether there's any change in numerical resolution effect in place for it. I'm not completely convinced. Well, Slidell doesn't believe in them.
Well, he doesn't see them, but I mean, the quantum grade rotation curve with the high resolution simulations, and he sees a much smaller cover.
Right.
So, you guys haven't tried to go after
Well,
that?
that's one of the things that bothers me with SPH in terms of the hydro of those flows. Right? They could have pay attention to a number of things that affect the hydro. Could be very sensitive.
Well, I guess that's hydro. I guess if there are no more questions, I guess we'll just go to cookies and thanks to the lesson.